And so next up we'll have Marco, who's going to tell us about clap. We can switch to mine if we need to.
I think I need to rest before the talk and was working. Don't suspend the Linux system.
But I use Linux as well, and it turned out okay. We've had quite a high percentage of Linux users actually present.
Then use the first laptops then.
I have
Can I
an
use
X1
yours?
Carbon. Yeah, yeah. I have an X1 Carbon as well.
No, but I had this first specifically.
Oh.
This one.
Oh.
It has this great property that if I watch a video on YouTube on Firefox, it shuts down. Only on Firefox. It's a productivity hack.
You haven't asked Claude Nicholas.
Can you hear me well?
Yeah.
No. Okay. Hello everybody.
No,
so
it's not working.
It's not working.
Yeah, the microphone isn't working.
Test, test. This one works.
I can yell to the end of the room. No, it's okay. I'm going to use this one. Okay. Blah, blah. All right. Okay. Hello again. I'm going to try to make up for the lost time. So I'm going to present. Okay, good. So I'm going to present clap. Some of you might remember clap from an older work a few years ago. This is quite different. Same spirit, same lesson learned, but more lesson learned. And this is going to be very oriented to verification and lean, like the other works in the session. So this is joint work with Nethermind, the formal verification team at Nethermind. They are still, so this is very much work in progress. So we are still doing a lot of work. They're doing amazing work. So thanks to them. So what is clap today? So clap is not anymore like an embedded language or a DSL. It's just a subset of lean. So today you will write circuits as a subset, it's just pure lean. Okay. Of course, lean is a very generic programming language, so you can write things that would not be expressible as an arithmetic circuit. And so, of course, if you write those things, we're not going to compile them. Okay. But if you restrict yourself to what can be what is an arithmetic circuit, then we should be able to compile it down. Then there might be some little problems on like limitations of our compiler pipeline. So maybe if you're using some, for example, for loop syntax, we still for in syntax, we still don't support. We might in the future. So, but I would say that we support a very large subset of what can be written in lean. And so right now, what clap is a meta compiler that is going to take your lean code and is going to produce constraint system and witness generators. So why this is kind of, if you have to remember one thing, remember this. Why this is the core idea and the core differentiating factors also with the other existing DSLs. Because if you, basically what you're going to write is very similar, or in my head it almost coincides with what could be an executable specification of your circuit. So what you're writing is not a builder, like we saw in the previous example, is not constraints, as you're going to see soon. It's really, I think, the cleanest possible mental model that you can have of a circuit, of an arithmetic circuit, which means that if you need to do verification on top of it, you're sort of starting from the best possible place. Like nothing of the compilation pipeline is going to pollute whatever theorem or properties you're trying to prove. So I'm not saying that it's going to be easy. So if what you're trying to prove is very complicated, if you have an incredibly optimized implementation and a very high level spec, well, there's still a big gap to prove. But the point is that any lean developer can do that, even if they don't know what a circuit is, or maybe AI is going to be able to do that, because there is less of the backend that pollutes the specification. This also, okay, an old topic from Club was automatic optimization. So again, like we start in a very clean state, so it's easier to do many of the optimization that we want to do. I'm not going to talk too much about this today because there isn't enough time. And okay, we care about, the reason to do this in Lean was because we want to verify the circuits that we write, but also that we want to verify CLAP itself, so the pipeline that is going to bring everything down to a constraint system. And so for every step for every transformation, we have theorems and properties to preserve that preserve the semantic of what we're trying to write. So the idea is that you will be able to take your lemma from the highest level specification and bring it down to the cryptographic proof system. All right, so this is very much work in progress. So I'm just gonna try to give you an idea of the status of what is there today and what is not there today, what is vaporware promises, and what is actually proved. So this was, again, last summer, I decided that I wanted to retry CLAP in Lean, so, and I did some experiments, and I ended up doing a complete redesign. I was planning to do the usual embedding, and then I ended up doing something very different. I'm going to describe this later. And right at that time, I need to thank Nethermind and Julian in particular for funding a grant from the Aptos Foundation to develop this more seriously and with more energy, with more people for 6 months. And we're almost at the end of this grant. And kudos to the Aptos Foundation that really believed in the project. That was not even an embryo at the time. It was really just, it was very, pretty much a sketch in my head. They believed in it, and Alin Tomesco has always been a very great supporter of our work. He's been following us and helping us to do actually the core of the grant, that is to replace their Circom R1CS circuits that are using their Aptos keyless products. This is kind of, I must say, it's kind of a hard nugget as a first exercise, because it's a lot of circuits. It's a lot of code, and they're the nasty kind, in the sense that it's not nice elliptic curves, or like this is like classic primitives. So like SHA and like, so a lot of bits, a lot of so pretty tricky. And just in size, like it's a lot. It's a complicated circuit with a lot of checks and a lot of ingredients. So this is what we have today, is that we rewrote all the circuits in Lean. And so far, so we have a first iteration of the compiler, but it doesn't scale to what we require. So I would say that we don't produce constraint systems yet, if that's what you expect to see. And we're just started writing specifications, so we don't really have done a lot of work on proving that the implementation corresponds to a specification. This is still a work in progress. So yeah, I wanted to give my usual speech about please do things correct by construct. I'm not sure I have a lot of time. But I just want to repeat that doing things that are correct by construction and building a system with formal methods at the design stage, it's absolutely not equivalent to building something using maybe a fantastic Rust pipeline, maybe a terrible amount of horrible code that produce some constraint system at the end, and then knocking on the door of a formal methods person and say, can you please fix this? Can you please prove that there is a specification of some kind? So even if they do, the result is not the same. You're not getting the same, okay? And I think the real world example that the grown-ups have shown us is that you can move from TLS 1.1 and to 1.2. There were a bunch of attacks, a bunch of researchers, cryptographers, and formal methods people, symbolic protocol, or like hardcore cryptographic primitives. So there were a bunch of attacks, and like the research community reacted, and they sort of fixed the attacks, but it was a catch-up game. And things changed completely with TLS 1.3. There was much more involvement from the beginning of the design phase, and the result is completely different. So I'm very happy that all these languages are coming up to do the right thing from the start. Okay, I'm not going to get too much into the history of how I got here, but the point is that I already did 2 embeddings of circuits in very different settings, learned a bunch of lessons in the process, and what I was trying to do with CLAP in Lean was to do something a bit different. And so let me explain so embedding, there's nothing wrong with embeddings, I love them, but when you try to do formalize things on top of them, they get a little bit in the way. So, and the point is that, actually, I mean, the previous presentation was amazing. It explained what I wanted. These slides much better than what I did. So what they have is it's a builder. What you, or I mean, what I already had in my previous projects. What your circuit ends up being a monadic builder that is going to build a deep embedding, or like if you don't know what that is, just a data structure that contains your constraint system. And so that's perfectly fine, and it works very well in practice. And I know people that have, so yesterday I was talking to the Tachyon guys, and they have a beautiful Rust code base that does this. So this can be done very well. The problem is that when you build a deep embedding, at every step you need to sort of convince yourself that what you build makes sense. So at every step you have a sort of well-formedness when you need to say, my constraints do what I think they do, and like my wires are all allocated correctly, and I'm not messing up, sort of. And you need to do this at every step, which is why we were saying in the previous slide, there was, actually I can show you an example for my terrible things that I wrote in the past. This is a piece of F-star, don't ask me why. So this is a very simple num to bits gate that is supposed to take a field element and explode it to bit. So this is what I was trying to, sorry? Sort of, yeah. I said, don't ask me why. So anyway, you can. It doesn't really matter what this is written in. The point is that you can see that this implementation is like 4 lines. It's pretty simple. It's nothing too fancy. This is this is like the pre and post. So you can see that again. It lives in a state monad. So I am carrying a bunch of state with me, which is what the usual. There's nothing weird. And so every time you want, basically up to here, this is craft just needed for the monadic builder. I need to say what I got was already well formed, everything was in bounds, and then I'm going to give you something that is still in bounds, and blah blah blah. Okay, this is not fun. And then this is the bits that it's interesting. And even in here, because I have a deep embedding, I need to always talk about evaluating things. I always have a denotation function that gives a meaning to the data structure. Okay, there's nothing wrong with this. This is like what you do in these embeddings, and it's perfectly fine. But when I did this, I said, okay, I don't want to write this again in my life. And the point is that I could fix this with a lot of automation, which is what they brilliantly did in the previous work. So in ZK Lean, this is completely hidden. There are tactics that do this for you. And it looks very nice. When we were looking at the Hort triple before, they were not this horrible thing. Okay, so there are definitely ways to do this properly and effectively. I just decided to try and do something differently. Okay, so the point is that proof assistants that are based on type theory, they are very good at, I'm not going to go into the carrier correspondence, but the idea is that if you want to prove something, you need to build a program, and this can be very complicated, and so they give you a bunch of facilities to build programs, to transform programs to programs, and so so this is what we call tactics. And I mean, these languages are meta sort of by construction. They need to be able to reason about their own programs. And so they also help you to do this correctly. And so they are sort of a great playground for certified compilers. Lean Meta is famous for being very, very good. In particular, at the same time, it's very expressive, and it can also be very efficient at what it does. And so I thought, let's build a meta compiler. So finally, let's look at the meat of the story. So what a CLAP circuit is, or rather, like what would you like a circuit to be? I don't know. If you ask me, I would say I don't want it to be a relation. First of all, like don't give me a relation. I would like it to be a function, and because we know that we're going to check something, that our circuit is going to add a bunch of assertions, then I know this is going to be a partial function. Okay, so I'm not too surprised that it's going to live in an option monad. And if I'm doing an intermediate computation, then I expect to receive a value, so it could be an option alpha. But anyway, if an assertion false, it's going to get a none. I think this is familiar also for people using Rust. So there is nothing lean specific about this. And then, of course, if a circuit terminates, then the only thing that it can return is an option unit. So it's going to say some unit. It's equivalent to say accept. Like all the checks passed, let's say the cryptographic proof system should accept. So if I want to write, and of course, this is just what it means to be a circuit. The number of inputs that needs to be statically known, and it has to be fixed. Okay, so I cannot just receive a list and do unbounded recursion to go through the list. Okay, so this is what. Sorry. Okay, so this is what very simple circuit. So you were laughing at James' example, but this is words. So this is just an addition. So yeah, so again, this is just an option unit, and I'm just receiving my arguments, and this is an equivalent of writing a constraint if you want. And as you can see here, there is no builder, there's nothing that regards compilation or anything else. This is a clap circuit, if you want to call it a clap circuit. This is a lean circuit today that clap can compile, okay? I'd rather say that. You can, of course, you're not limited to using field elements. You can use the structure that you have in lean. So this is just lean. This is not something that we defined. And as long as you use something that is bounded. So they have to be vectors of a known size. What things that are not in the subset? Well, again, no lists. No, you cannot return something from a circuit. It doesn't make a lot of sense. And there's a little more subtle things. Of course, you cannot branch on an input and say, in one case, I'm going to do a huge circuit, and in another case, I'm going to go a small circuit, okay? But these are not limitations of clap. These is limitations of circuit. These are not circuits to begin with, okay? So there are a few gotchas when you write these things. Okay, so just I want to underline the fact that there are no constraints and there are no witnesses yet, okay? So when, for example, E0 in this case, it's a basic construct for us, okay? And the definition of E0, I'm very sorry there is a monadic arrow here. This is a limitation of our pipeline right now. This should not be monadic. Like E0 is a pure function, and the definition is exactly what you have in your head. If the expression is 0, then 1, else 0. Okay, that there is nothing. This is the definition of E0 that is used here. And the point is that this is a function that returns a value. So there is no inverse, and the B is an output, is not an input that you're going to put in a relation. Okay. All right. So now that I have my executable spec, I can of course execute it, so I can test it, or I can go a step further and I can try to prove that indeed my check add is the same as the lean addition. Okay. And again, the important thing here to remember is that this is as simple as it can be. Like clap is not adding anything on top of it. I'm going to repeat it again. So a circuit sort of coincides with this denotation or with its executable specification. There is no state mono, there is no constraint system, no witness generation, there is no embedding, and there is no evaluation of that embedding. Okay. This is the thing that I expect the user to write. So these executable specifications, and then the rest is going to be derived. Okay, just to make it extra explicit. So to have a look at the architecture. So now we're going to look what happened after you wrote that. What is it that we're doing? So there is a first phase that I call the front end. I don't know, to make it sound like a compiler, where we are reducing the circuit to basically a list of very basic operands, like the E0, for example, or EQ0. And then once we have that, then there is the part where we split. We produce a constraint system and a witness generation. And so this part for this part, we have a complete equality. So for this is done using the lean simplification framework. So we have proof of equality that is basically done for free by lean. And then from here on, we define our own properties of soundness and completeness. I'm going to explain more, but just to give an overview, we prove that the constraint system is sound with respect to the reduced circuit, and this is our refinement. okay? While for the completeness, we proved that if you take the constraint system and the witness generator, and you put them together, you use them together, then they're perfectly equivalent to the circuit that you wrote at the beginning. All right, so so let's go in the front end now, and let's see what I meant with simplifying. So this is so the circuits that I gave you before, they were very simple. Sorry, this is a bit more of a more interesting example. So what if there is some control flow that is not obvious, like here, for example. Here there is a little loop I can fold, and I want to check that all the elements of a vector are 0, and I want to accumulate this. So this, like off the top, like here on the spot, I wouldn't know maybe how to translate it to constraint, and I don't have I don't want to write an algorithm that is going to do that. Okay. What I can do is I can just use the sim framework from Lean to actually reduce this into this form. And so what happens is that, so a critical thing, so for many simple things, they can just be reduced. It's not that hard. The key ingredient is to notice that the vectors, we know the size of the vectors. Okay? If we know this, we can write some simprocs that are going to explode them into things of known size. And at that point, simp can really simplify all the way down. Okay? And it can give us this completely unrolled and flattened version of the circuit. Again, these things, we mark them opaque for simp, so that it's not going to go in. So for them, at the level of the circuit, we have, like I said, the very intuitive and simple definition. So if the expression is 0, then, but this, we're going to compile them later. We're going to transform them into something very different in constraints. And so we don't want them to be unfolded and unrolled. Okay, they need to remain little black boxes so that we can do our own transformation later. So what we get here is flat linear sequences of black boxes. Okay, and this is so this step of reduction is currently the bottleneck that we have. The thing that we need to try to make to scale to reach the size that is required by Aptos. And okay, I'm happy to talk about this. This is not a sort of a secret sauce. Like I'm happy to talk about this. It's just that it's very technical and very Lean specific, and I don't think everybody's going to care. I'm going to skip the automatic optimizations because so far we haven't done a lot of work on them, so I don't have data to substantiate my claims. But I mean, we are planning to recycle some of the old optimization that we did in previous versions of CLAP and see if they're as effective. They were over Plonk, so the question mark is, are they going to be as effective on R1CS? We'll see about that. So we can go in the back end. So right now, what you will find in the code base is FOSS representation. So what we're trying, we go down to a deep embedding that is higher order. So we transform the reduced circuit into this parametric higher order abstract syntax, which is something from that I think Adam Chipala is the most prominent user of this and that has popularized it. And the idea, so this is a higher order representation. So it simplifies a lot of things, like working with bindings. It can be very cumbersome. So this definitely helped a lot. I'm not sure this is going to stay in the future in the sense that it's a bit tricky to use, and I don't think it's going to scale to so it forces you to work in a sort of a CPS style, which is nice for some things and very annoying for other things. So I think the plan is to move also this backend to become a meta compiler. Okay, but this is not done yet. So the theorems that we proved are over this FOSS syntaxes. So because it's a bit unreadable, I try to write an example where this is what we would do with the new meta compiler that is not written yet. Okay, so this is vaporware. Okay, but there is a one-to-one mapping, very simple, from the FOSS syntax to this. It's just that it would be impossible to go through in a presentation. So to give an idea, an intuition of what happens is that so this is the same reduced circuit that I showed earlier that was unrolled from the fold. So what we do is very simple. So each is 0 is exploded into 2 constraints, which is what you expect. So one is here, one is here. And then the EQ0 was already a constraint, so we don't touch it. It stays the same. Of course, like at the beginning, so this function, the original circuit used to take 2 inputs. Now we still take those 2 inputs, but we need a bunch of extra stuff. So there are these 4 extra inputs that correspond to these 4 guys that we don't know how to compute. So I expect somebody to give them to me. Okay, otherwise I don't know what to do. And that somebody is going to be of course, the witness generator, which again is going to compute like the result and the inverse. The result and the inverse is going to put them in a list or a vector, and that's what's going to be produced. So I think this is not surprising in any way. But this is just an example of how the pipeline continues. And so what is that we proved over this? So what again, soundness is I'm going to repeat it even if it's boring or obvious. So the point is that we want the constraint system to not be more accepting than the circuit. So if you give me a garbage signature, if the constraint system says, yes, this is great, and the original circuit said, no, this is a garbage signature, then we have a big problem, okay? So it cannot be more accepting. It can be less accepting, okay? So a constraint system that always fails is very safe. Not very useful, but very safe. So the problem is that so you saw earlier, the original circuit took 2 arguments, and now the constraint system takes a bunch more. It took like, what was 6, right? So how do you compare a function that takes 2 arguments with one that takes 6? So the intuition, the way I like to think about this is using simulations, or what is used in, I don't know if you're familiar with compilers, how you prove equivalences of compiler passes usually is with simulations. So if we try to imagine this as a label transition system where a function is going to take an argument. This is what you see this is the event that you see, and it's going to step to a next state, and then it takes another argument and step to a next state. So here we can imagine this is the circuit, and this is the constraint system. They will take the same argument and they will step, and then there will be a problem at some point because the circuit doesn't need auxiliary arguments. It can compute its own. While the constraint system is going to need some help. It's going to need an inverse, for example. So, and in this case, we need to we cannot force them to work in lockstep. So it cannot be a strong simulation. It has to be a weak simulation. So we need to allow this guy to step while the other one is waiting. Okay, this is to give you an intuition. In practice, the way this is written is as a relation and is a relaxation of functional extensionality. So you can see that just receiving an argument and stepping into a state that is still related, it's just what functional extensionality does. So we just need to relax it on asymmetrically on one side. So one side can step more than another. Okay. And so the other modification relaxation that we need to do is the fact that at any time the constraint system can fail, and there is no problem. And actually it must, in the sense that, so in the previous case here, let's imagine that the constraint system is waiting for the inverse, okay? It gets the right one, it actually gets an inverse and can step, and we can continue. But it has no guarantee that it's going to receive the real inverse. Maybe it received garbage. So in that case, the only thing, the right thing actually to do is to stop and to halt, okay? So in a sense, we need to allow it to fail, otherwise it cannot possibly be in the relation with the circuit. So these are the two relaxation that we do of functional extensionality to prove the soundness. And like I said, we can always cheat and say that CS that never accepts is sound, and so that's why we like completeness. We would like to make sure that it actually does something useful. And so this property, it's actually simpler in the sense that if you take the CS and so the constraint system and the witness generator together now, and you put them, the one that we produce, and you use them together, then they're completely equivalent to the circuit that you start with, okay? All right, so just a final word on Aptos and the work that we did. So like I said, so Aptos keyless is a fairly complex protocol. We only focus on the circuits that they have. So the statement that is, frankly, is a simple part compared to the rest of the story. But the statement itself is pretty complex because it has to work over. Again, the main problem is that you need to work with the objects that come from another tech stack. So you have whatever Google produces a JWT, and it's going to be JSON, and you need to parse this JSON. There are a bunch of tricks and attacks that you can do in parsing this JSON, so this is expensive and complicated. It's also pretty hard to actually to formalize, so we're trying to really find ways to how to explain this in a terse way as a specification. And then there is the problem is that if they're going to sign something, it's going to be signed with the SHA-256, so now you need to deal with SHA. And if they sign something, it's going to be with RSA. This adds quite a bit of complication. So what we did was, again, rewriting the full relation, the statement has been completely rewritten in Lean. And we have we prove the soundness and completeness of the gates. So there are a few basic, very ridiculous gates that are needed in CLAP, and those I prove sounding complete pretty easily. I'm very proud of that. And then the hard stuff, like the binary decomposition and the multiplication modulo large prime, this is mostly Julian's work. And the first one is completely done, and the second one is mostly done. And he actually found also probably, I want to jinx it, but an optimization to reduce the number of constraints needed for this. So this is pretty, I consider this done. And then there is a lot of work left to do. So for now, we can only test our circuits. So we still need to prove something more interesting about them, about the functional correctness of the circuits, and of course, extract them to something that I can fit to a cryptographic proof system. That's it. Questions?
Yeah, yeah. I was curious, or I didn't get the part where is0 was compiled into something that is non-deterministic or that uses a witness, or at all. I didn't get at all how you do this automatically. You know.
So the point is that you can. Okay, so in the current implementation, this gets transformed into a deep embedding. So I have this FOSS syntax that represents this, like it's a mapping one-to-one. It's not, there's no transformation. It's just a bit uglier to look at, okay? And then I can step through that. So I have constructors for each one of these guys. So I can step through them and I can say, okay, whenever you see one of these, you actually produce 2 of these, okay? That's all there is to it. I would like to write meta programs to do these steps. So the meta programs in Lean, you basically can look at this as an expression. So Lean can inspect its own syntax. So I would just say, let's go to meta. This is now just an expression. And if I navigate the expression and it turns out that I find one of these guys, that a particular function application that is called 0, then I will replace it with the, so it's a very mechanical process. That's it. There's no, and the same thing for the witness generator. You just generate does it answer?
Yeah.
Ah, okay.
Just speak up. Yeah.
I can repeat the question. Yeah.
Yeah. So I have 2 questions actually. One is if you have any plans or intentions to expose witness hints to the circuit.
Witness what? Sorry.
Witness hints, like the ability to inject the witness value into the circuit to the circuit authors.
Okay, so that's a good question. Sorry? Why for RSA? In which case, I don't know. The thing is, okay. Let me answer the question, and then I can. The thing is that you can already do this. So you saw there is an EQ0. So I can check an expression. Okay. So whatever you want to. So this is basically this is all you need. So I can take an input, and I can check that corresponds to something. Okay. This is how you do this. So maybe I don't know if it's clear for everybody, but the point is that there are the main trick that you do in circuits is that some things are expensive to compute. And so you just ask for the result and you check, and sometimes it's cheaper to check just the result, okay? So which means that I can transform any function that takes one input and gives you one output. I can transform it in a relation, becomes a relation. So you have 2 inputs and no output, okay? Do we agree on this? The point is that every time you do this trick, you get in trouble, and you need to prove soundness and completeness of this thing, okay? So you can definitely do it, but you're basically, I would be moving the responsibility of soundness and completeness to the user, okay? So you can totally do it. So you can take I can write now a circuit where you give me the inputs, and I check them for you, but then if it is sound and complete, it becomes your problem, and you need to prove it as an extra property. So this approach in CLAP, is basically saying, I'm going to take your whatever it is that you need to do, I'm going to make it a gate, I'm going to prove soundness and completeness for you. Because I mean, the point is that in my experience, this does not happen every 5 minutes. There are a few very important cases that you need to deal, that sort of hot paths in a circuit where you really need to do this, because otherwise some things are impossible. But there are not a million of these cases. So you write, so for example, for the whole keyless, we had the 2 gates that I showed. So one is num2bits, which is kind of obvious, and the other is fbmul, which was a bit more annoying. And that's all we needed to make everything else work. So we proved soundness completeness of them, and then that's it. So you can absolutely do that. It's just that you're pushing more problems towards the user.
No, but like let's say I'm a library author that like I've come up with
Sure.
With a new subcircuit that I would like others to be able to use, and like this actually happens. Like
Sure, all the time. Like if I try to verify something that is not keyless, I'm gonna find a new, I don't know, sometimes you call them oracles. You will find more of these guys for sure.
okay, so like, how do I express this nicely in CLAP? I guess is the question. Like,
So
as a library author, like what's the API that I expose to?
exactly. So this is another motivation to. So right now in the backend is an embedding. Okay. So I have like maybe I should have answered better your question. I really there is actually an inductive where I say case 1, case 2, case 3. I have my constructors. Okay. So I can write a compiler that goes through them and compiles. The problem is that okay, if you come up with a new thing that you want to use, I need to add a constructor in there, and I need to explain how to compile it. And this is it can be, I mean, it's not very extensible, what I'm saying. Like I need to extend the language sort of for you. While with the meta compilation pipeline, if also the backend is meta compiler, then it's much easier. If you give me 2 definitions, and you give me a proof of the proof of soundness and the proof of completeness, then I can plug them in pretty easily, and I can extend the compiler for you and compile your case. And you can also say, I don't care about completeness. You don't prove it. Okay, so like the overall guarantee of the compilation pipeline is weaker, but I mean maybe it's okay for your case.
So the compilation is done by metaprogramming, and when you do the compilation, does the metaprogramming also generate a theorem proving the refinement relation? And then this happens every time you do a compilation, so there is no general theorem for like, it's not a verified compiler, but it verifies itself every time you compile it. Okay.
Yeah, it's a proof generating compiler. Yeah, I don't know why that is particularly useful. I mean, the point is that this is sort of comes from, so for the front end, this comes from Lean. So because we applied the simplifier, applying the simplifier is just basically applying a bunch of lemmas and theorems repeatedly, and they carry their own proof. So this is simp at the end of a run is going to give you a large proof of all the things that it used. And then for the backend, basically there will be, if we do it in, so right now there is a theorem that says, because right now it's a concrete path. So it's a function that takes the reduced circuit and produces the constraint system. And we have a theorem that says, if you apply this function, then you get the soundness property. Okay. So these are just proved over the correctness of that function. If I were to do it as a metaprogram, then the metaprogram would read the circuit. It would write a constraint system, and then it would also write a proof that the two are connected. Okay.
You mentioned that it's invalid if like you branch on secret data or something like that. Since you have a meta compiler over just like Lean ASD, have you thought about adding checks that like the user does this by accident?
Yeah, that's a great question. So right now what we do, we have a type class over the field so that we can abstract. So for example, you don't have this decidable equality. So if you Lean is going to tell you like, no, this if is not, the guard of this if is not okay. So it's not even that we don't compile it. Lean doesn't let you write it. This is sort of, it's not clear if we're going to keep with this because basically so having a type class that abstracts a bit some things gets a bit in the way of proving, because every time you want to punch through the abstraction to do proofs, you sort of have to say, no, by the way, I have an instance of this, or you can open it in this way, unfold. So this is a bit inconvenient. we could write, like you said, in Meta, we could just write a linter, something that goes through your code. As you write it, it's going to give you a warning, like, are you sure you want to write this? This we're not going to be able to compile. So great suggestion.
I just want to add two small things. It's not actually a question. I just wanted to add that for a bunch of small circuits, particularly relating to the parsing, we've already actually been able to formally verify them, just as a small point, because that wasn't entirely clear. And the other thing is, thanks to Leo's recent work on the simulation monad stuff, symbolic monad, sorry, rather stuff, we very much expect that the meta performance issues will be resolved shortly. Sorry, I hope you don't mind I added that in.
No, I didn't want to nerd with too many details about sleep. But yeah, no, absolutely. We're one of the first users of SIM-M.
The signal shot stuff is all using SIM-M as well. So there's some integration with, so MVC Gen is going to use SIM-M and Loom 2.0 as well. Yeah, it was Ineos uses MVC Gen. That's the link. Do you want to switch over?
Yeah.
And then I guess there was a point about RSA, but it's I guess it doesn't matter too much.